Hello. So we just have a couple more examples to finish up. Sorry about the awkward ending in the last one. I lost my record button, so I couldn't see if I was recording or not. I did. Okay, so we just finished the torque problem. We have just a couple of problems dealing with the parallelepiped. And in this particular one, we're supposed to find the volume of a parallelepiped using adjacent edges. And so, we did one problem where we were given the three vectors that make a parallelepiped, but now we're not given them. So we kind of have to at least get this set up, and then it's the same as the other problem. So we've got these adjacent edges, and what that means is the following. Let's say that this first dot will be P. Then we have an edge here that moves out. That'll go to Q. Then we have an edge that goes up, and we have an edge that goes in. So Q, R, and S. Now to give this a little bit of depth, we need to draw in the parallelogram that is formed by the adjacent edges of these vectors. There we go. Oops. There's one more. Okay, so now we can see a parallelepiped here. And so it looks like we need to form three vectors, and the three vectors should always start in the same place. They should be the three vectors that kind of define the parallelepiped. So what I'm going to do is I'm going to let A equal PQ, B will equal PR, and C will equal PS. Those are going to be my three vectors that define the parallelogram. So using things we've done before, remember you always take the later point and subtract the earlier point. So we'll take the components of Q and subtract the components of P. That means in the first component I have 2 minus a negative 2. Second one I have 3 minus 2, and then 2 minus 0. That simplifies down to 4, 1, and 2. My second vector, PR, I have 1 minus a negative 2. I have 4 minus 2, and negative 1 minus 0. And that simplifies to be 3, 2, negative 1. My C vector is PS. So just take the components of S and subtract P. We get 3 minus a negative 2, 6 minus 2, and 1 minus 0. And that simplifies to be 5, 4, 1. So these are our three vectors, and we have to remember that the volume can be the magnitude of A dotted with B cross C. And we can calculate that by just finding a determinant with the three vectors A, B, and C in it. So we calculate that first, A dot B cross C, which is the determinant with A in the top row, 4, 1, 2, B in the second row, 3, 2, negative 1, and C in the third row, 5, 4, 1. This will give us 4 times the determinant with components 2, negative 1, 4, 1, minus 1 times the vector with components 3, negative 1, 5, 1, plus 2 times the determinant with components 3, 2, 5, 4. Okay, keep calculating. We get 4 times 2 minus a negative will be plus 4, minus 1 times 3 minus a negative will be plus 5, plus 2 times 12 minus 10. So this is 4 times 6 minus 8 plus 2 times 2. So it's 24 minus 8 is 16 plus 4 is 20. So the volume is equal to the magnitude of 20, which is just 20. That's our volume. So the only difference between this one and the previous one is we had to create our vectors first. After that, it's the same problem. The last problem is, how would we show, using what we've learned, that the following vectors are coplanar? And we're given 3 vectors. Now, you wouldn't know what to do if you don't know what coplanar means. So like, there are issues if you don't know the vocabulary, and this is your first time probably even seeing that word. So let's define it. Coplanar vectors all lie on the same plane. And if all 3 vectors lie on the same plane, that means that we can never get height for a dimension with those 3 vectors, right? We could get an area, but that's about it. So to show that vectors are coplanar, we must show that V, the volume of the magnitude of, I guess I'll use U, V, and W, U dotted with V crossed with W is equal to 0. If we don't get a 0, if we get like a non-zero volume, then that means that we are able to form a parallelepiped with the 3 vectors, which means they are not coplanar. Okay? This would imply coplanar. Okay, so let's calculate that. Our U dotted with V cross W is equal to the determinant with U in the first row, 1, 5, -2, V in the second row, 3, -1, 0, W in the third row, 5, 9, -4. This gives me 1 times the 2 by 2 determinant with -1, 0, 9, -4, minus 5 times the 2 by 2 determinant with 3, 0, 5, -4, minus 2 times the determinant with 3, -1, 5, and 9. Go ahead and calculate those. This gives me 1 times 4 minus 0, minus 5 times -12 minus 0, minus 2 times 27 minus a negative, that'll be positive 5. Okay, this gives me 4. This gives me plus 5 times 12 is 60, so I get plus 60, minus 2 times 32. That gives me 64 minus 64, which is 0. Therefore, the vectors do not or cannot form a parallelepiped and must be coplanar. Okay, this is a lot to take in. I'm sorry to do all the applications in a video, but my hope is that then you can kind of take your time going through them instead of going through them with the speed that we would have to in class. Please, please, please write down your questions, bring them to class. I am happy to answer any and all of them. And I will see you on Wednesday.